In this video, we're going to learn a little bit about some of the characteristics of acids and bases, something that we've talked about in the past, but we haven't gone into in great detail. Let's start out with a little bit of historical perspective. Svante Arrhenius was a Swedish chemist slash physicist. This is a stamp honoring the 100th anniversary of his birth. You can see he was born in 1859, so he did most of his work late in the 19th century and then early into the 20th century. He did his doctoral thesis in the study of electrolytes. You remember electrolytes are substances that when you dissolve them in water, they conduct electricity. He used the term ionization, and much of what we know about solutions came from the work of Svante Arrhenius, but he also defined an acid, and his definition of an acid is a substance that ionizes in water to form the hydrogen ion. So you can identify an acid, an Arrhenius acid as it's called, because when you put it in water you get hydrogen ions, and they're also recognizable by their formulas because they start with the hydrogen, although we have to be careful because some acids, notably organic acids, do not start with hydrogen. And then a base is anything that, according to Arrhenius, ionizes in water to form hydroxide ions. So again, you can identify an Arrhenius base because it ends in OH. This is a very simple definition of an acid and a base, but a very powerful definition of an acid and a base, and one that we'll fall back to pretty often. Now, as time went on, other people studied solutions in acids and bases, and these two gentlemen, Bronsted and Lowry, redefined definitions of acids and bases because of their a little broader perspective on what constituted an acid and a base. So let's have a look here. According to the Bronsted-Lowry model of acids and bases, an acid is a proton donor and a base is a proton acceptor. Now, a proton donor is a fancy way of saying that it gives hydrogen ions. So to donate means to give up, and a proton, remember, is just a hydrogen ion. You take away the electron and you've got a proton, and then if something will then accept one of those hydrogen ions, it is a base. Now this is a broader definition of base than before. So let's think about how those things are different. Those definitions of acid and base are different than what Arrhenius said. And one thing that is of note here is that we do not need water necessarily in this model to get an acid and a base. Now, as I say that, then as we go further forward and into the next video, we will look at some examples of Bronsted-Lowry model ionizations, and every one of them is going to have water in it. But it is not necessary. As long as something will give a proton to something else, it is an acid, and as long as that something else will accept it, it is a base. So if we have an acid and it donates a proton, then the particle that's left over is called the conjugate base. And the word conjugate just means the one that goes together with it. So we have an acid, and the base that we get afterward is the conjugate of it. What makes it a base? If you think about that for a minute, you see that after the acid has donated a proton, it now has a space to accept a proton, and that makes it a base. And so after a base accepts a proton, then it's called the conjugate acid, and it's an acid. If you think about that again for a minute, and it's an acid because it will then give up that hydrogen that it has just accepted. Okay, so we're going to move forward in the next video and look at some examples of how we can apply the Bronsted-Lowry model to some situations.